Hello, everybody. Let's get started. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. Welcome to the MIT Mobility Forum designed by the MIT Mobility Initiative. Today, I'm really excited to have Professor Jelena Notaros join us, talk about photonics. Right. Within transportation, of course, there's a lot of excitement about autonomous vehicle, as well as the ADAS system, where there's many debates on should we use a LiDAR, radar, or camera, or some combination. And within LiDAR, the distinction between mechanical LiDAR versus solid-state LiDAR. And today, it's my great pleasure to have Professor Jelena Notaros to come here, really talk about photonics, but specifically on the silicon photonics for solid-state LiDAR and its application in autonomous vehicles. Particularly, she will describe to us the emerging class of the silicon photonic system that is an integrated optical phased array OPA system, which enable the control of the light in a very compact form factor at a very lower cost and in a non-mechanical way. So before I formally introduce Professor Notaros, I do want to reinforce the norm of this forum, which is everyone contribute one idea. So for all the audience, I invite everyone to type into the chat either a comment or a question to Jelena. So during the third phase, we'll engage the audience for the question answers here. Also, thank you for typing your organization and the location time into the chat, so we get a sense of the audience here. But also, I want to do a quick poll, which I just launched, to get a free sense of what the degree of engagement in LiDAR in this audience. So I just launched it. So the first one, you have direct engagement doing R&D in LiDAR. The second one is direct engagement, but in the sense of applying LiDAR to the autonomous vehicle system or other topography, AR, etc. And third one is indirect involvement. And third one, I'm just curious out here. Right.
That's a great idea to have the poll. I was actually going to start out by asking who had some experience in.
Oh, great!
LiDAR. So
great,
this is perfect.
Cool. Yeah, thank you. Yeah,
Tone.
because the topic is quite specialized today. I want to get a flavor here.
Yeah.
Okay, there's about 70 people participated. So we'll end in 5 more seconds. All right, so I'll end the poll and share the result. Right. So 6% direct on R&D of our LiDAR, 10% on its application integration with AV, 18 on indirect, and 60 for just curious. Thank you. Yeah. All right. So Professor Jelena Notaros is the Robert Schillman Assistant Professor of Electronic Engineering and Computer Science at MIT. He's a PI in the MIT Research Laboratory of Electronics, RLE, and also a core faculty member of the MIT Microsystem Technology Laboratory, MTL. Her research focuses on the silicon photonics device systems and applications. She was one of the top DARPA risers for 30 under 30 listees, and MIT Herbert and Dorsey Grier Presidential Fellow. Also, just in yesterday's MIT news, actually your research is spotlighted. MIT engineer created a chip-based tractor beam, the one you saw in the Star Wars, right, for biological particle.
Yeah.
No one has created a silicon photonic-based optical tweezer capable of trapping the microparticles over a millimeter scale distant before. So this is a major progress there. So congratulations for your research to be really spotlighted there. Now, without further ado, let me give the forum to Professor Notaros. Jelena, please.
Awesome. Wonderful. Thanks so much for the introduction. Yeah, as mentioned, I was actually going to start out by asking who had experience in LiDAR and in photonics. So the poll was perfect to set the stage. So it seems like a lot of people are coming in, maybe just curious about LiDAR technology, about how we could use it for autonomous vehicles. So I love to have that context. So I think the slides actually will work perfectly today. I was going to start out first, just introduce everyone. Jinhua, can you see my mouse here too?
Yes, we can. Yeah.
Perfect. I just want to make sure. So I'll start out with an introduction to silicon photonics. And what does silicon photonics technology actually mean? We'll then get into LiDAR, and we'll start with the motivation in general for LiDAR within the context of autonomous systems. Why are we interested in solid-state LiDAR as opposed to kind of mechanically beam steering LiDAR? different types that will arise. And then I'll get into really how you can use silicon photonics, and specifically this idea of integrated optical phased arrays to demonstrate these solid-state LiDAR systems. And I'll talk through some of our group's recent results briefly at the end. And then I'll just very briefly mention some of our other work in the space of optical phased arrays in case anyone is curious for the last few minutes. So first, an introduction to silicon photonics. So for those of you that are not familiar with the field of silicon photonics, the general idea behind silicon photonics is that we want to repurpose CMOS fabrication processes and tools to create chip-based optical devices and chip-based optical systems. So on the bottom here, you can see a cross-sectional view of a silicon photonics process that we've developed in the past. This is in collaboration with SUNY Poly in Albany, or AIM Photonics, if anyone is familiar. So here on the left-hand side, if you're coming from an electrical engineering background, you would recognize this device. This is a bulk CMOS transistor. For those not coming from the electrical engineering background, what a transistor is, of course, the baseline electrical component that governs everything that we do in the microelectronics world. It's going to be our electrical switch. And what that transistor looks like is you have some silicon here, patterned with very small dimensions, on the order of nanometers. You're going to have doped silicon. That means you take the silicon and you dope it with different dopants. And then what that allows you to do is to place metal contacts down into contact with the doped silicon. And then when you apply voltages across those metal contacts, you can actually get switching of your transistor. This is kind of a baseline explanation of the building block behind microelectronic circuits. Of course, you put all these transistors together to actually get your functionality. Well, in silicon photonics, we want to take all this development that's happened in the microelectronics world and apply it to optics. So we can take the same layers that you would normally use to create your transistor here, and we can repurpose them to create optics on chip. So for example, we can take that silicon, and we can now create what's called silicon photonics dielectric waveguide. Again, if you're coming from the electrical engineering world, perhaps you can think back to your electromagnetics class. When you talked about waveguides, you probably talked about dielectric waveguides. Well, what this dielectric waveguide is going to look like is, this is a cross-sectional view. This would actually be a long piece of silicon kind of going into the slide here that would be on your chip. So if you're actually looking down on the chip, you just see this long rectangle kind of going along the length of the chip. And then you can actually get laser light, and you can what's called couple into this waveguide, and the waveguide is going to guide the light on the chip. So once you have light guiding on the chip, then you want to be able to modulate. You want to manipulate the light on the chip. So how you do that is you take your silicon, you extend it out to the sides, and then you dope the silicon, or you place little heaters on the silicon. And now you can place metal down into contact with those doped regions, and you can actually cause modulation to the light in the waveguide. So instead of the light just passing through, now you're going to cause a change to the phase or the amplitude of the light as it passes through that waveguide, and that's actually how you're going to manipulate the light on the chip. Then, of course, we don't want to just manipulate the light on the chip, we want to interact with the surroundings. So, for example, you can see here, we can pattern periodic structures to actually emit the light up and out of the chip and actually interact with the surroundings of the chip. Using these little nano antenna devices. These dimensions are all on the scale of tens or hundreds of nanometers. So the silicon photonics, what that allows us to do is to take, optical systems that were once very complex and large. So for example, you could take a system that once took up an entire optics table, like a very meter by meter kind of size system, and integrate it onto a completely flat millimeter scale chip that would look just like the chip that you have in your smartphone on your laptop for electronics, but now I would actually be doing optical functionalities. We're also taking advantage of standard CMOS processes to fabricate these devices. So you're going to be able to take advantage of wafer scale fabrication that you normally use with CMOS. So on the left here, you can see a photograph of a 300 millimeter, or about 12 inch, so about the size of my head, wafer that is fabricated on a standard CMOS foundry line. But now, instead of electronic devices being on that wafer, now we're going to have our photonics in there. And what that allows us to do is have a scalable way to fabricate photonic devices and systems. And of course, that's going to make it lower cost than having mechanical components and also more stable. And by doing all of this, we can enable new functionalities as well by integrating things on chips that you wouldn't be able to do before with fiber optics or bulk optics. So there's many applications that we have in the field of silicon photonics. One of the most traditional ones is using silicon photonics for data communication, for datacom, telecom applications. That's really where this field of silicon photonics boomed about a decade ago, and when I started working in the field. But one of the systems that's really come to light now is the idea of, can we actually create solid state LiDAR sensors using the silicon photonics technology. So that brings us into LiDAR. So let's talk about the motivation for LiDAR in general, forgetting about silicon photonics for a moment. Then why would you want something like a silicon photonics solid state solution for LiDAR? And then I'll talk you through what those devices actually look like. So as many of you are probably familiar, if you look at an autonomous vehicle nowadays, you'll see this large sensor. It's slowly getting smaller, but you'll see the sensor sitting on top of the car or maybe kind of distributed across the car, and that's the car's LiDAR sensor. And traditionally, what that LiDAR sensor does is it sends out a pulse of light. That light pulse goes out into the surroundings, it reflects off the surroundings, comes back, and then based on the time delay of the light pulse, how long it takes for the pulse to come back, the sensor can calculate the distance to the object that it was reflected off of. And then that entire sensor spins around mechanically and keeps shooting out these pulses of light, and the light keeps coming back. And then the sensor can process a full three-dimensional depth map of the surroundings of the car. So why, that's the general idea behind how a traditional LiDAR sensor works. But why are we interested in LiDAR compared to, for example, radar or other types of sensing modalities for autonomous vehicles? Well, the real motivation for this comes up when we go to higher and higher tiers of autonomy. So if you talk to, automotive companies, there's different tiers, different levels of autonomy that are kind of standard in the industry, right? We start with just kind of basic sensors that allow you to maybe have a little bit of help with staying in your lane or stopping when a car stops quickly in front of you. Maybe now, you go to higher tiers of autonomy, you're going to be able to get help with parking your car. But to get to full levels of autonomy, the requirements on the sensor suite that are used in your autonomous vehicle are going to become more and more stringent. And kind of one of the metrics that you hear going around for full autonomy, usually you hear this metric of, can you detect a target that's about 20 centimeters tall at a distance of about 200 meters away? So how you can think of that is, what if there's a car and it loses a tire, and there's now a tire in the road about 20 centimeters tall, and you need your car to be able to detect that tire far enough away, 200 meters here, so that your car has enough time to react to this object being in the road. So these are the kind of metrics, the detection goals that are really required for total autonomy, for fully autonomous vehicles. So now the problem becomes, radar works really, really well, and it has served us so well for many decades, and for a lot of the autonomous features that are out in cars right now. But when you actually look at these very stringent metrics, 200 meters out to detect an object that's only 20 centimeters tall, you need a radar aperture that's about 4 meters. That's like larger than the car itself. And the problem is, right, like if we want to get to these more and more aggressive detection metrics, the radar aperture needs to become huge, right? Twice the size of a car about. If you look at what aperture size you actually need, what physical aperture size you would need for a LiDAR sensor to meet that same metric, it's only going to be about 1 millimeter aperture size to get that same exact detection, that same exact resolution that a 4-meter aperture would require for radar. That's just a fundamental limit of electromagnetics. That is why, if you're familiar with, like current higher end cars, right, that are starting to get more and more autonomy, you see the emblem of the car getting larger and larger. You see I think BMW, right, the emblem is just getting huge on the front of the car. And the reason why is because the emblem is actually where most cars have their radar aperture. So the companies are making the emblems larger and larger because the aperture size is getting bigger in order to be able to detect with higher resolution further out. And I see someone just popped in the chat something about, another approach is to increase the frequency of the radar. Absolutely. Effectively, if you increase the frequency, right, the aperture size becomes smaller. But really, right, we need to be able to increase the frequency quite a bit, all the way up to optical frequencies to get a more reasonable aperture size for some of these really intense metrics. So the challenge, of course, though, we have this dream of really high resolution sensing, but the challenge is, what is the form factor going to look like for these LiDAR sensors? And I think a big reason why initially they weren't being adopted as much is because a conventional LiDAR, kind of how LiDAR looks like now, is essentially how radar looked like 50 years ago, right? Radar now looks like a chip that's a solid state solution. It has more intense modality. You have MIMO radar, all of this development that's happened on the radar side, and LiDAR just hasn't been around long enough. There hasn't been a lot of development. So conventionally right now, what LiDAR looks like is radar 50 years ago, right? You're going to have a mechanical component that's spinning around. This is going to be able to degrade over time, right? The accuracy of the pointing of the LiDAR beam is going to degrade due to weather conditions. Historically, these sensors have been really expensive because of these mechanical components. The price is continuously going down, but if you're actually putting together bulk optical components, that's going to be more expensive than just a chip solution. And most importantly, when you do this pulsed modality, we call that time of flight LiDAR, you're really limited to the detection range, how far out you can detect before you're overcome with noise. The signal to noise ratio is not so good when you do this pulse modality for LiDAR. You need to actually go to coherent methods, for example, frequency modulated continuous wave methods for LiDAR, to be able to get out to the couple 100-meter range that's really required for these autonomous vehicle metrics. So we really need to move to solid state LiDAR to get to the point where LiDAR is a compelling solution for autonomous vehicles. A solid state LiDAR, right, you're going to have completely electronic beam steering. It's going to be just a compact, a little millimeter scale chip, completely flat, very lightweight, low cost to fabricate if we use standard CMOS fabrication technologies. And I think the one important thing to remember is when we talk about LiDAR, I think if you talk to automotive companies, the idea isn't that LiDAR is going to replace radar in cars. What they really want is a suite of sensors where you're going to have radar and LiDAR and camera vision technologies all working together to ensure that we have a very safe environment for humans to be in these autonomous vehicles and be able to operate over a wide range of conditions, going from fog, reflective surfaces, to be able to get these high resolution features out of the environment. So we really need all of these sensors to come together. So before, how do we actually create one of these solid state LiDAR sensors? The really important thing here is how are we going to scan that optical beam around non-mechanically? And that's where this concept of integrated optical phased arrays using silicon photonics comes into play. So the idea behind optical phased arrays borrows heavily from the radio frequency counterpart. If you are familiar with electromagnetics or radio frequency systems, you've maybe heard the term phased antenna array. the optical phased array borrows heavily from that. So the general idea in the RF domain is if you have a single antenna, that antenna is going to kind of emit everywhere. But if you have multiple antennas and you feed these antennas coherently, the signal that emits from each of these antennas, if it's coherently fed, are going to work together to form a beam, a directed beam in a certain direction out of this array of antennas. And then if we go in and now we control the phase, or in other words, you can think of it as the speed of the signal coming out of each of these antennas, you can actually do some interesting beam shaping of this beam that's emitted out. So for example, here in this little animation, we can see if the signal kind of emits sooner out of the antenna over here and emits later, or in other words, is phase delayed out of the antenna over here, you have this what's called phase front that occurs. You can see you have signal coming out sooner on this side, later on that side, and now this beam that's emitted out, that's formed by this array of antennas is going to kind of curve and be directed, be steered in one direction out of the array, in this direction. If we slow down the light now on this side, speed it up on that side, we would see this beam now curve off to the other direction. And that's this idea of non-mechanical beam steering that's been around for, like 100, 200 years in the RF domain, led to the Nobel Prize, a ton of technology in the RF space, but is very, very hard to do at optical wavelengths. So that's where silicon photonics can come into play. We can now show these optical silicon photonics based optical phased arrays, where we're going to have our millimeter scale chip. We're going to pattern tens of thousands of little optical antennas on that chip, and we're going to feed them using silicon photonics circuit to enable these optical integrated phased arrays. So this idea of an optical phased array, I wanted to shout out to my other colleagues in the field. We've seen some nice work all the way going back about over a decade ago from the Batz group at Ghent. They showed the very first demonstration of one of these optical phased array systems. But I think back then, the technology of silicon photonics wasn't yet mature. So, they showed a system with just a couple of antennas, fabricated in a clean room in the university. But it wasn't until the last several years that this field has really blown up and taken off, because I think that in general, the field of silicon photonics has matured. So we're able to show these silicon photonics systems now scaled up and with more relevant metrics to really take advantage of the scaling. So a lot of excellent work coming out of many groups, many colleagues around the world. I'll focus in today, though, on the work coming out of our group at MIT. So before we get into some results, I thought it would be interesting to talk you through what an example of one of these optical phased array systems could look like. So here would be a top view of an optical phased array. If you're kind of looking down on the chip through a microscope, this is, of course, a cartoon version of what you'd see. You'd have a single waveguide that's going to come from a laser either on the chip or off the chip. That single waveguide is then going to be split out using a series of 1x2 splitters into an array of waveguides over here. The waveguide is then going to be periodically perturbed here using these little blocks of kind of wider pieces of silicon. What that allows you to do, here we have another cartoon, if that light comes in and you kind of periodically perturb the side of a waveguide, what happens is that at each of these perturbation points, the light is going to scatter. Some light will continue, some light will scatter some more. So these periodic perturbations on either side of the waveguide are going to allow the light to scatter up and out of the chip. That's going to be our baseline antenna element. We then have many of these antenna elements kind of coming together. That's what's going to allow us to create that array of antennas that's going to make up our optical antenna array. Now, how do we actually control the phase to each of those antennas? If you remember on the very first slide, I showed you how you can dope certain regions of the silicon to enable modulation of the light. So you're going to place one of those little phase shifters or phase modulators on the waveguide before each antenna to control the phase of the light that's emitted out of each antenna in also an integrated way. So you could apply a voltage to each of these little phase shifters and control the phase. then if you remember from that animation we looked at earlier, if you kind of advance the phase on this side, make the light emit sooner on this side, you delay the phase on that side, that's what's actually going to enable you to create that phase ramp and enable beam steering out of this system. This is now going to get into a little bit more detail probably than needed, but the other direction where you can do beam steering, you don't want to just steer in one direction here, you want to also steer in the second direction. To do that, you actually put in a different wavelength of light into the system. That's going to affect the effective period of these grating-based antennas, and that's going to change the emission angle out of the antenna. So you have wavelength-controlled beam steering in one direction, voltage-controlled beam steering in the second direction. So again, a lot of excellent work coming out of many groups in the field, but I'll talk you through some of our recent results from our group here at MIT. So of course, before we show a LiDAR system, we need to be able to fabricate these silicon photonic devices. So if you're familiar with AIM Photonics, I mentioned them earlier as well, we work together with SUNY that houses AIM to develop a 300mm wafer fabrication process for fabricating these silicon photonic systems. And then that process that we developed with them back a number of years ago is actually what turned into the now commercially available process for fabricating silicon photonics that most colleagues in the US use. So after we develop this platform, we have to design all the different optical phased array architectures. So I just talked you through one of those splitter tree based architectures, but there's so many more that we could show. Here's just a recent example for some of our work coming out in collaboration with Jonathan Klemkin's group at UC Santa Barbara, where there's many different ways that you can show these optical phased array, many different architectures to demonstrate them. We also have to think about what the laser is going to look like that's going to power this system, so we can design integrated lasers that are fabricated on the same computer chips as our photonic systems. We can't just have the lasers operate at one frequency. Like I mentioned, you have to scan the frequency to get beam steering the second dimension, so we can have tunable lasers on chip. If we just thought about designing the photonic components and not how we drive them, this wouldn't be a real product. So we also have to think about how we're going to integrate electronics with our photonics to do both the driving and the data processing of these signals. So here we developed a 300mm wafer scale fabrication platform, again in collaboration with SUNY, where we have a 300mm photonics wafer and separately a 300mm CMOS electronics wafer. We flip the two on top of each other and pattern through oxide vias to enable direct driving of the photonic components with integrated CMOS. And then we can use that platform to show these optical phased arrays, but now driven with a co-designed CMOS circuit on the same chip. So, we kind of glossed over it. I thought it would be a little bit too much detail, but if people are interested, we have to not just emit the beam and scan the beam around, we also need to be able to have the beam reflect and come back and actually do LiDAR processing on those beams. So again, I'll very briefly introduce you to how that works. I have some supplementary slides if people want to get into this in more detail later. But we have a transmit optical phased array. That transmit array is going to emit light off the chip. The light is going to reflect off some target and come back to a receive array. And then this is really allows us to get that coherent detection, allows us to have a longer range detection, is we do what's called coherent frequency modulated continuous wave, or FMCW detection on the receive side, where we take that received light and we beat it with a local oscillator to get enhancement of the received signal to beat out the signal to noise ratio that we would normally be killed by. That's really the limitation of prior LiDAR, why it wasn't able to kind of kick off sooner. And then, most recently we didn't just show one of these LiDAR systems that emits one beam and brings it back. We can actually design systems where if maybe we have two features that are of interest in the scene of this autonomous vehicle, we can emit multiple beams, have the beams come back, and then actually process them completely passively without using any electronics, using this new architecture that we developed. So that's just a blast through some of our work in this space of integrated optical phased arrays for LiDAR. In the last minute, I'll maybe just talk you through some of the other research that we have here in our group before we then move to maybe some discussion. Our group is working in general and optical phased arrays for many different applications. So for example, we're also working on chips where we have an array of 1,000 of these little optical phased arrays that projects three-dimensional holograms on a completely transparent chip to create an augmented reality solution that doesn't require any bulk optics. That required creating transparent wafers, these CMOS wafers, but being able to actually see through them. So a whole new wafer fabrication platform is the first transparent 300 millimeter photonics process. We also have to create new types of modulators when we're working with visible light for this AR application. These are integrated liquid crystal modulators that enable a reduction in the length of the modulator by 2 orders of magnitude compared to comparable ones. We recently had a paper where we're using these optical phased arrays to actually create a chip that projects some kind of beam and uses it to cure 3D objects to have a handheld chip-based 3D printer. Junho just mentioned, we just had yesterday a paper published where we're again using these optical phased arrays to create focusing beams and actually trap cancer cells and do manipulation of these different biological particles. If you're looking at bio applications, you want chips that aren't just going to sit on the surface of the body, but are going to conform to the body. So we have flexible wafers, flexible chips. I think related to vehicle applications, I think this would be kind of interesting if you're needing some kind of conformal LiDAR sensor, for example, that could apply there too. We also have some work in quantum computation where we're using these chips to emit light off the chip and interface with different types of qubits, in this case, trapped ions, and then also doing underwater communications. Maybe just because the topic of this forum is specifically for mobility and vehicular applications, even though we're working on these different technologies for other applications, I thought maybe I'd connect them to where it could come into play even for mobility related work. So for example, one problem with LiDAR sensors is they have a hard time seeing through fog, and that's because they're operating at infrared wavelengths. So if you wanted something that could maybe do LiDAR underwater or in foggy environments, you need to drop down the wavelength. So you would want to use something where you're actually using the chips that can, transmit light underwater. So you need to drop down to visible or blue wavelengths instead of infrared. Again, the flexible wafers, if you need something that's going to conform to the outside of a curved part of a car, you could think about that for future LiDAR sensors. And then I think the AR transparent wafers, there's a lot of discussion. We're not specifically working in this space, but just kind of throwing out some ideas to get thoughts flowing. A lot of discussion, on heads-up displays for vehicles. So can you create transparent displays that are going to project information in a car? So some of this work could also apply there. So yeah, I hope that this is interesting to give you a little bit of an introduction to LiDAR sensors, silicon photonics, and how you can use silicon photonics for solid-state LiDAR, and then just briefly touch on some of these other areas we work on. Of course, I could never give a talk without giving a big shout out to all my wonderful students in our group whose hard work really makes all this possible. So with that, maybe we can move to discussion and questions.
Yeah, wonderful. Thank you so much.